Hello again. And so the century changes from the 1800s to the 1900s, and as sometimes is the case, just by the accident of the calendar, we get new ideas in the beginning of the new century, and this was certainly true in this case. A German physicist mathematician named Max Planck was dealing with the Blackbody problem and ultimately came up with an idea that energy, electromagnetic energy, is transferred not, as Maxwell suggested, in waves, continuous waves, but in bursts of energy. Now, this is a very significant departure from what we would think is actually happening. And given that light can be perceived is a wave phenomena, such as what Young taught us, and Fresnel, and also just even with simple spectrographs, one kind or another, the behavior is very similar to mechanical waves. But Planck was not necessarily convinced that this was a true phenomenon of nature, and he saw it more as a mathematical convenience in his mathematics solutions to these problems. But then, of course, comes the next person in our story, of course, the famous Albert Einstein. And Albert Einstein was the first person to say, I think at least, that this quantum idea was not just a mathematical convenience, a solution engine, but was a true phenomenon of nature. And showing this applied to the photoelectric effect, came up with a pretty straightforward explanation of the entire process. And so this video chronicles the real beginnings of the idea of quantum mechanics, the work first of Planck and then of Albert Einstein. Max Planck was a middle-aged German physicist at the turn of the century. He had done other work related to earlier aspects of physics, and that wasn't, of course, really the point here. He was the first person to really take and initiate an idea of quantization of electromagnetic energy. And he did this in his solution to the Blackbody equation. Now, Planck is considered the father of this, and perhaps with some justification, and a lot of times the birth of these types of things is a bit murky. Planck certainly advanced the idea of quantization, but in many people's estimation of his work, he did it as a mathematical convenience and not as a true phenomenon of nature. Nevertheless, the idea was put forth that an electromagnetic energy comes in pulses and not in a continuous waveform, and it changed the world. In the late 1800s and in the beginning of the 1900s, Max Planck was working on the Blackbody problem. Now, I'm going to vastly simplify his work, as his work involved thermodynamics and some fairly difficult mathematics, so we're going to keep things under control here. If we imagine an oven, so this is a insulated structure with a very small port where we can detect what's going on inside, but by detection is not going to materially affect what's going on. Now, if a oscillator, and what we could imagine is a vibrating electron, emits a light wave, it goes across the other side, that electron here will absorb that, cause it to improve its vibration, and by its vibration re-radiate this, and this will go back and forth a lot. Now, of course, in real life, you're going to have rays going in different directions and so on. Let's not complicate it. So what you can look at is, well, what would actually cause this to happen? What waves are going to work here and what aren't? If we take a random wave like this and it goes across the oven, so this is this distance here, if you will, is this distance here, okay? We're just using it as an example. If the wave goes across like so and ends at the wall at a maximum, and when it's absorbed, it's going to get damped out. No different than when you're skipping or something like that. When the wave comes to the end of the line, if you are driving it, it needs to be a maximum. If it's going to be reflected, it needs to be a node, a minimum. So what happens is, if you end up with a case like this where it comes as a maximum, these get damped out, these get absorbed, and the resulting wave you get is basically just nothing. It doesn't show very much. However, if we do achieve a case where we have a wave whose wavelength is, or the length of the wave in this, the length of the oven, pardon me, is a multiple of half the wavelength, then the reflection is going to be inverted and will do this. And when you look at this, the situation appears static. So you have the wave being propagated and it's being reflected, and this goes on and on. Now, of course, if it's a mechanical wave, we have to still stimulate it because there is friction. But in the case of the oven with electromagnetic radiation, if you have a perfect absorber and a perfect emitter, this will go on forever. And anyhow, this phenomenon is known as a standing wave because it appears to be something you can see. And this principle is used not only here, but in musical instruments and many other situations. Now, these waves will stay manifest in this situation. And so what happens now is you end up with a situation where there's allowed wavelengths. Okay? So the wavelength maximum, we said it has to be a multiple of half the oven size, would be equal to 2L. Okay? And L being the length of the oven here, for example. Okay? Now, we can have, of course, that's lambda max. So lambda now can be some integer of this. It can say, okay, well, let me think now. We could have 2 lambda equals 2L, for example, and cancel this. And now we'd have this case here where we have lambda equal to the wavelength. We could end up with lambda is equal to 3 over 2L, and so on. And so these are known as harmonics. The point of all this is that while 3 over 2 is okay, you cannot have 1.56 L. Okay, you can't have these fractions. This is not permitted. This will lead to this situation. And so as a consequence, we end up with distinct waves that are allowed in this situation, not just any one that you want. Now, with that being said, it's a bit of a leap, conceptually, for Planck to look at this and say, okay, well, instead of continuous waves going back and forth, okay, we're going to have the energy sent as a burst. So not as a wave in this sense, but that the energy will come as a burst, as a function of the frequency of the wave. And he said that this burst would be equal to the energy, as he called it a quanta in his time, is equal to h, a constant, times the frequency of the electron. And he said you can have multiples, so we could put n in here. Now n has to be a natural number. It has to be a number that's like 1, 2, 3, 4. It can't be some decimal. And this allowed for a more mathematically convenient solution. Now, I understand that this explanation is not going to be anywhere near what you'd find in the theory if you study this in university. And this is because the mathematics and the thermodynamics is just simply beyond where we are just now in our studies. So as a consequence, I think that we'll stop with that. But basic point here is that by looking at this oven problem and looking at how waves would propagate, he recognized there was discrete ones allowed, not everything. He also began to recognize that at least mathematically it was easier to solve the problem if the energy was transmitted in a pulse versus a continuous wave. And this is a major departure, and of course Planck himself saw this as a mathematical convenience, not as a true phenomena of nature, given how well waves seem to represent the physics of the day.
This graph is just a brief one to show the departure of a theorem that they didn't expect called the equipartition of energy. The black line is what the theory suggests if you extrapolate at higher temperatures and energies, what you would get. And what we find down at the very low temperatures and small circumstance, the quantum world, is that the red line shows how things actually behave. And this was a departure that was not predicted necessarily initially, and this is something that Planck had to assess and handle and incorporate into his solution. And of course, this was a big beginning to where he got in his work.
So let's just have a look at what Planck was trying, what came out of this. This isn't too bad. So first, our Blackbody graph once again. The intensity, how bright the light is. This is the wavelength. So in other words, this is basically like color. So how bright are the red? How bright is the green? How bright is the blue? How bright is the ultraviolet? How bright is the infrared, etc. at any specific wavelength? That's in effect what a spectrum truly is. So when you see a rainbow or whatever, that's what you're detecting. But in the lab, we generally do them as graphs because we want to see really what's going on. Now notice a few things is that as the wavelength gets longer, the light has less energy. If we remember Planck's equation here, we'll just keep the simple version, equals hf. We also know that c is equal to f lambda, so this gives us E is equal to hc over lambda. So therefore, as we have seen, the energy then is inversely proportional to the wavelength, which is what we've been detecting. So as the wavelength gets longer, the energy gets less. So the energy increases as the wavelength gets shorter, which is what you see here. Rayleigh-Jeans predicted the low energy side, Wien predicted the higher energy side, but there was no conciliation between the two theories. When Planck finished his derivation, he arrived at a description of the Blackbody curve using this description here. And it models the experimental work perfectly. So let's remind ourselves of what these variables mean. None of this is that difficult, and it's just a matter of understanding what the notation means. So what we say first is the Blackbody intensity, that's this model here. So this is calculating this, okay? And it's doing it for a specific wavelength and for a given temperature. So what we're going to do in advance is we're going to choose a temperature. The temperature of this thing is not going to be changing. It's going to be a fixed amount, like a light bulb's filament or something to that effect. The light bulb's on, and so this will be, in effect, this is going to be a constant for a given spectrum. Okay? That's important to remember. So really, all we're going to do now is use the lambda, and we're going to scale across here. We're going to start at either 0 effectively or at a large number, and we're just going to evaluate this thing across, and this will plot our Blackbody curve. Now let's look at what the variables mean. Planck's constant, okay, speed of light, the wavelength that we're dealing with to the 5th power, and then there's this interesting expression here in parenthesis. Now, you may have seen and you encountered the constant e to the x, which is equal to, where e is equal to 2.7172 and so on. It is one of the constants of nature in mathematics. And so exp just simply means e, okay? Because the exponents of e sometimes get very involved, and so if we write them like this, then we can use a larger typeset to show them. So once again, we have this Planck's constant times the speed of light divided by the wavelength times the temperature, and again this is in kelvins, okay? And this variable k here, this is the Boltzmann constant, okay? And calculate this out, and this is why we use computational engines, and you will get this very nice curve. And this models very nicely what we do in the lab. So this is the first time that we've been able to show Blackbody radiation as a theoretical function that would model completely the work of the experiment. And this was the first success of quantum theory. Now, the main point to stress here with Max Planck is that as a brilliant scientist, there's no question. But his interpretation of his solution was that this was a mathematical convenience. It was not quantization of electromagnetic radiation was not a true phenomenon of nature. This was simply just a convenience that allowed us to fix this problem. However, we will see that it wasn't that simple.
Albert Einstein was an obscure patent clerk in Zurich, Switzerland. He had been born in Germany, was not a particularly good student as a young age, primarily because of the autocratic approach of his educators. When he was put into a less militaristic school, so to speak, he began to blossom. And this work rolled out ultimately into his personality being more of a pacifist, non-regimental type person, and ultimately floated around and ended up at the patent office in Zurich, where he would see new devices that would come in and evaluate if they have sufficient originality to them that they could be granted a patent. Now, I suspect that business wasn't all that hopping in those days, and he had time to read and think, and he had a young group of other fellows who were keen to discuss physics-related ideas. And in this banter, he began a remarkable career. So first in 1903, he published a mathematical treatment of Brownian motion. So I'm not sure in your chemistry if they still do it or not, but if you take pollen grains and put them in water and put them under a microscope, you'll notice that the grains vibrate around. It's proof that the molecules are hitting one side a bit more than the other side, and that this is a suggestion that these things are actually there. And Einstein is the first person to put a statistical argument to that. However, his truly spectacular year, well, the first one of them, of a few, was in 1905, when he published his special theory of relativity, where he took the results of the Michelson-Morley experiment and reinterpreted them. Instead of saying that time and space are fixed, but rather that the speed of light is fixed and time and space must conform, and that all observers in all reference frames will see the speed of light as the same number. Well, this is a profound departure from what are perceived norms. And at the second point, he took the mathematical treatment of the Photoelectric effect and advanced the point that Planck's idea was not a theoretical, just a theoretical answer, but a true explanation of the phenomena of nature. Now, Einstein was a nobody at the time, and such a radical suggestion cannot really be done so easily by an established scientist because their reputations are at risk, which they've spent years building. But a nobody has nothing to lose, and they can be bold, and Einstein certainly did that. And so he published both these papers in the German version of Physics Annals, and the ideas didn't catch on instantly, but this began the second explanation of a phenomenon that had not been explained before using the quantum idea.
So this is a graphic of a experiment done by Lenard in the turn of the century, which was attempting to characterize the photoelectric effect so that we could then begin to think about the theoretical aspects of it. We have here a mercury vapor lamp. Mercury vapor lamps are useful because they produce a spectrum that starts in the infrared, goes right through the visual and into the ultraviolet. Now that's more efficient, I suppose, for lighting rooms, but of course with the ultraviolet presence, it is a significant biohazard, so you have to be very careful if you do an experiment like this one. This tube is evacuated, okay, and this because electrons and other charged particles don't flow very well if there's air in the tube, so we have to take all the air out. We have two different kinds of filters we can put in the way here. The first one is what we call a neutral density filter. Neutral density blocks all colors equally. On the other hand, the second filter is a line filter. This allows a narrow part of the spectrum to pass and blocks the rest. Here we have what is called the anode, and the metal, the shiny metal surface, this blue here, okay, which is inside. And then we have our electrical setup here and our ammeter. So we have straight line through, we have one battery that's going to cause the current to flow one way, another battery that's going to cause the flow to go the other way, a variable resistor that will control the potential difference you create across this, and an ammeter to measure the current flow. And so when you connect it, even straight through, if you have ultraviolet, you get a current flow. Not very much of one, but it does occur. However, we can reverse bias this or forward bias. We can enhance the effect or we can reduce the effect. Now, I'm going to rub some stuff out here and let's look at what's going on. We have energy from the photons. Actually, let me rub it out and we'll make a summary of that as we go. So we'll just rub out the details here. So if we look at the energy, we have the energy of the light. Okay, and when the electrons are released, we have E sub k. This is the kinetic energy of motion of the electrons. And finally, we have the energy of the metal. So this is the energy required to leave the metal. Now, just by basic idea of conservation of energy, you would get something that looks like this. The energy of light is all you got. So the energy of light minus the energy of the metal, okay, will equal the kinetic energy of the electrons. However, when you're trying to theoretize this thing or do an experiment, this is a problem. Okay, so let's look at each of these points here. How do we measure the energy of light? Well, Planck has taught us that we can take these photons and we can measure them individually. So we could take the line filter and that would choose certain photons, so we would know that. Okay. The energy required to leave the metal. We don't know what that is. And how would we measure the kinetic energy of the electrons? So we have two problems here. Let's step back just a second, though, and look at how this behaves. If we remove the line filter completely and just work with the neutral density filter, the energy of a wave is proportional to the amplitude, its height, squared. And so, it doesn't, based on that logic, it doesn't matter if the light is red, blue, or green. It depends on how bright it is. What they found when they did this experiment is if you limited the light to the red light, you could make it as bright as you wanted to. And we had absolutely no effect over here. But a small amount of blue or ultraviolet light would give a profound effect over here. And it was shown that the energy of the light was proportional to color, and it was not proportional to brightness. And this, of course, agreed with Planck's idea. Everybody was kind of flailing about. Albert Einstein came along and said, listen, you know, Planck used this mathematical convenience of E equals hf, but this is actually what's happening. This is the exact explanation of the photoelectric effect, that the energy of the light is a function of its frequency, or hence its wavelength. And this is going to give us a relationship here. And so he looked at this particular situation, and he saw that we have these three basic energies, but two of them are hard to measure. We didn't even thought of this one before, the energy of the metal, and measuring the kinetic energy of electrons. How would you possibly do that? Well, fear not. This apparatus will help us do this. So let's have another, we'll just rub this out and we'll stare at it again. If we turn around here and we use our battery, we'll produce a potential, a voltage, V stop, okay? And this means no electrons, okay? Now, we would imagine that the energy due to the metal is constant. The energy from the light is also constant. It's a given color, okay? So that means then that V stop times the charge, to make it an energy, is going to give us the kinetic energy. So Einstein then says the following. He said, well, okay, so we're going to have, I'll do it, we'll do E V stop. The voltage is the energy per unit charge. To get this to become a total energy, we must multiply by the charge, which is the elementary charge, equals the energy of the light minus the energy of the metal. Now we're getting closer to where we need to go, because we know a lot of stuff here. And the only thing we don't really know, if we assume we know Planck's constant, is this energy of the metal. So let's look at this again. So we're going to rub this out. And we'll extend it. So the energy of the stopping, as I already said, is going to be EV stop. So that's no problem. We have the energy of the light is equal to HF, which is equal to HC over lambda. And the energy of the metal is unknown. So now we have EV is equal to HC over lambda plus this unknown constant. Our variables are going to be V and lambda. This is chosen from the line filter, and this comes from the battery. So we will modify this slightly. V is equal to HC over E times 1 over lambda equals, or sorry, plus whatever. I guess it's a negative. Well, it doesn't really make a difference, but we'll make it negative to be consistent here. It's negative because it's
energy we have to give away, phi over E. So now we can say this one here is a variable. Let's use another color. So this is a variable. This is a constant. This is a variable. And this is unknown. And so this gives us an equation with one unknown and a way to compute these things. And Einstein called this concept here the work function. And this gave us a sense, and this is a property of metals. So if we put silver in there, we get a certain work function. We put aluminum in there, we get a different function, and so forth. And this gave us this explanation. It is a masterpiece because of the fundamental idea that he said, okay, I'm going to use Planck's idea of quantization of electromagnetic radiation, the fundamental principle of quantum mechanics, and employ it to the results of Lenard's experiment, and we get this result. And so now, in 5 years, we've now had the quantum idea has shown us a theory for blackbody radiation that works. Now we've had an explanation of the photoelectric effect and an equation to describe it, and recognizing that this property of metals, of how well they hold onto their electrons, all using a quantum idea. Okay, and so now within 5 years we had this new thinking has given us the solution to two intractable problems of the 1800s. This is pretty powerful. Just to look ahead a little bit, it is interesting here though, because we have light, which has no mass, interacting with a metal, ejecting an electron, giving this electron kinetic energy. And that means we're changing its momentum. Now momentum is simply mass times velocity. So how can something that has no mass give a particle momentum? Now that was for another day, but we can begin to see this duality factor starting to show up.
So there you have the new ideas starting to come. What's interesting here, of course, is that the quantum mechanics is not something that was discovered, metaphorically in a bathtub as someone yelling eureka and running down the street. This was, of course, something that was counterintuitive, that was not something that was visible in nature so much, was microscopic, and the clues and evidence was very confusing and difficult to rationalize. And so the fact that we had this thinking so long ago is amazing given the technology of the age. And so first Planck and then Einstein came along looking at the world a different way. Now, of course, Albert Einstein's famous for looking at the world a lot of different ways, and this was just one of them. He was given the Nobel Prize in 1921 for his services to the subject of physics, but if you look at it in more modern terms, he probably deserved, 2 or 3 Nobel Prizes for some of the work he did over the years. But that's a secondary point. However, you see first the mathematical preparation, and then Einstein showing that this in fact manifests well in nature. And of course, this gave the quantum idea enormous traction because it was the only explanation for the photoelectric effect. It wasn't just one of them, it was the only one. The other methods didn't provide anything satisfactory. And of course, as events continue now, we'll see that this idea is further adapted. Not so much because it was elegant, not so much because people liked it, but because it worked, in the sense that it gave explanations to problems that simply had no explanation in classical theory.